Right. Um, Good morning, it's early morning, and I would say welcome to this wonderful class. It's going to be a very brief introduction. We'll focus most in this course to introduce you on how to solve some problems under binary operations and the clarity of the definition and explanation should help you to solve any problem that will come out from this um, space of mathematics. So please, I would really like you to look at the definition of binary operations that you see there on the board, because it's going to help you a whole lot to understand what the word binary operations, whenever you see problem connected to this field of mathematics, yeah, you should know what you're asked to do. You answer any problems under this topic based on what you are asked to do, according to the principles and rules that would be explained to you here. Okay, let's start. From the introduction, a binary operation is a rule. I would like to highlight the key things uh, and explain each and every one of them accordingly so that you will not see yourself wanting in trying to solve the problem. A binary operation is a rule. So I would like to underline the word a rule. Is a rule that combines two elements, don't forget two elements, from a set. Let me say from a set, a particular set, it can be natural set, it can be a set of real numbers, it can be any set. And you said that is user-defined set, someone that decides to twist around using a particular set of these interests to produce another element. I want you to look at the word another element uh, from the same set. I would like you to also really look at the same set. It's whatever element that is going to be produced out must be the element that also belongs to the same set. Without wasting much time, I want to quickly write a set. We have a set A, B, C, for example. Now, all the entries of this set are known as elements. All the entries, what you see here, are known as elements. So when I'm talking about element, I don't want to look at something that is quite different from, you know, what the definition of the set is, this particular topic is talking about. So, uh, so binary operation is about uh, you collecting some elements. It must be two elements. That's why we have the word binary. So we collect two elements from a particular set. It must be from a particular set, a set, and you combine them according to the property or the operator. Okay. So the operator, if the operator will produce another element, and that element is we call, let's say I collect them, let's say A operator asterisk B, and when collecting these two elements, A and B, and combining them by the operator asterisk, then the operator asterisk produce an element, let's say C. If element C still belongs to the same, let me call the same as, then we said that the binary operator has obeyed the property, and so therefore it's defined in that sense. Okay. All right. So that is what this course is all about. So the most important thing that I would like you to look at again is uh, that a set, I mean, the binary operation is always on a particular set. Is always on a set. You can't define it in a neutral ground. It must come from a particular set. and the operator must be unique, and it must give you a function, like a function. Let me give you a very simple illustration of what I'm talking about. I'll give you a single variable function. Let's say we have f of x equals to 2x plus 1. It means that there is a set that x is defined, such that if you impute it into this function, it will give you an element f of x. So for example, if I say f of 1, it will give me 2 times 1 plus 1. So, and this will give me 2 plus 1, and that gives us 3. So I can easily say that f of 1 from this set is 3. So this is a rule. The rule says you multiply 2 to 1 and add 1 again to have the element of f of 1 from a particular set, which one was defined. In this case, we call that set a domain. Okay, so in this other problem, this particular one binary operator, since we are dealing with 2 elements, I can say that let's define the function of binary operator as x of y, and we collect 2 elements xy from a particular set. And then let's say the operator is 3x plus y minus 1. And if I say that x is 2, if x equals to 2 and y equals to 3, then I can say f of 2 comma 3 will be equals to 3 times 2 plus 3, then minus 1. And of course, this is 6 plus 2, and that will give us 8. Now, we have that f of 2 comma 3 is equals to 8. All right. This is a binary operator. It's a binary operator. So you can look at the rule here, 3x plus y minus 1 as the rule given. And this set of rule is, in this case, is like saying multiply 3 to x, and after that add y to the result. Then when you get everything, subtract 1 from everything. So whatever thing the result will give you, if it is in the set where 2 and 3 were extracted from, if like for example we have 8, if there is 8 in that set, that means the operator, whatever what we write as that operator to be, is as it has obeyed the operations of, or is one of the operator of the sets, or it helps to generate the element that belongs to that set. All right, enough for a lot of talking. Okay, so to cut a very long story short, I would like us to look at the properties of this particular problem we are referring to. All right. One of the properties that we should be talking about here is the properties, the closure law. So we can briefly call it closed law. Let's say we have a set. What this law means is, if you have 2 elements, let's say A asterisk B, that is, remember, the asterisk is an operator. Remember, the asterisk is an operator. An operator, there can be addition, multiplication, anything that is given. And we can say S is still a set somehow, where A and B will still have other elements are being extracted from it. Now, if by combining A with B through the operator asterisk, if by combining A operator B or A and B with respect to the operator asterisk, it generates an element, let's say C. If this C or this element that this operator generates from the collection of or by the combination of the A and B is, if this element C is also in this set where this A, B are, then we say that the operator asterisk here is closed. We say that the operator asterisk here is closed under that expression. Let me give you a particular example. Let's say we have a set of natural numbers where you have 1, 2, 3, 4, instead of counting numbers, and so on. And I define this set by an operator asterisk, and the operator asterisk is combining this as, let's say, A asterisk B is equals to let's say A plus B minus 2B. So if I collect any element from the set, if I collect any element, let me not define it like this yet. Let me not go this far yet. So if I say, let me try addition of this element. Let's say I collect 2 elements from this set, let's say 2 and 3, and I add them, 2 plus 3, it gives me 5. And if you check, by counting this element forward, after 4 supposed to be 5 and so on. So we can conclude that addition plus sign is an operator in the sets N. Or more specifically, we can say that plus addition is closed under the set N. Similarly, if I say 2 times 3, that gives me 6. If you keep on counting this number, you realize that we have, generating the element of this set, we have 6 somewhere. So on that note, we can say that multiplication is also closed in the sets. That is what it means. If a collection of 2 elements from a set generate another element that belongs to the set, the operator that connect those 2 elements are said to be closed. That is what closure law is all about. Another one that I want to talk about is commutative law. By commutative law, or property, he said that if, like, we collected 2 elements, let's say still define the sets 1, 2, 3, 4, 5, 6, and so on. If we collect 2 elements, A asterisk B, and we interchange and it gives us C, and we change the position of A to B and B to A, let's say B asterisk A, and it still generates the result C, then we say that that operator is a commutative operator, or it is commutative. Say that it is commutative. If after changing the position of the elements, they don't generate the same element or the same results, then we say that it is not commutative. I really want to take note of that. So the last, another one that I want to talk about is identity property. Identity property says that there is an element in the set. Let's say I define a set S, which is A, B, and so on. There is an element inside of this set such that if you add any of these numbers, say A, it will still give you the value A. You add B to it, it still give you the value B. If there is such element in this set, then such element, for example, if it is E, is called an identity element. And because the identity is called identity element, and because the identity is under the operator plus, we can call it identity element under addition. Or simply additive identity. Similarly, if you have an element also from the set, say E, so that, for example, we multiply any of the elements that are in that set, and they still generate this element, the operator still generates the same element that is multiplying to a particular element. We can still call that element an identity element. But since it is under multiplication, we can call that multiplicative identity. So take note of that. Just take note of that. It will really help us a long way to solve some problems when we dive into the practical way of solving problems in this course. So like a practical example, if we still consider our natural number set, it's a natural knot. You can, okay, the set continues. If I pick 0 plus 1, it gives me 1. 0 plus 2, it gives me 2, etc. On this, I can say that 0 is additive identity. Similarly, if I do 1 times 0, it gives me 0. 1 times 5, it gives me 5. 1 times 10, it gives me 10. So on this note, we can call one multiplicative, can call one multiplicative identity. In algebra, these are the two most common These are the two most common um, identity elements that you really see so very much in the field of algebra, at least for this stage. All right. So finally, we talk about the inverse property. This one is simple. If you have a set S that defines some set of element A, B, C, D, and so on, if you pick two elements and collect them by the operator asterisk, and it give you an identity element, then is we can say that B is an inverse of A, or that A is an inverse of B, depending on which element you take as the real element and which one you assume to be the inverse element. So what am I saying in context? In this context, I mean that when you have two elements such that the collection of both of them by an operator give you an identity element, one of those elements are inverse elements. These are the most important and must look at properties. The one that is not very common, but must be explained, is associative property, which is the last one before I start solving problem. Associative property. I won't talk much about this. Associative properties says that if you have some element A asterisk B asterisk C, and you change the position, and you realize that if this is equals to, let's say, D, an element D, and you still also do A asterisk B asterisk C, and this time you combine this first before you allow this one to come into the result of this. If this also still give you D, then we say that whatever the operator is and the elements, they are associative. All right. Without wasting of time, I want to believe that what I'm trying to explain right now has given you the clarity. But what I can put to this is to make it more simplified, assuming A asterisk B asterisk C, I bound this first. I want to deal with this. Assuming that this give us K, then we say that K asterisk C give us D. And we do the same thing, A asterisk B asterisk C, and we bound this first. Assuming B asterisk C is giving us M, so we combine it with A and the results to give us, let's say, D. So because these two results has given us the same, operation has given us the same result, we can say that the collections of this element under this particular operator is associative. Don't forget this. You will understand it better when you try to solve some practical problem. Okay, with all this explanation, I would like us to solve some problems that I have taken time to check them out for you. And before we start solving this problem, I would like you to pay attention to details of the explanation that I gave to you from the beginning of the session. This one says the first problem that we want to solve. A binary operation asterisk is defined on the set of real numbers such that two element A asterisk B is equal to A plus B plus AB. We are asked to find an identity element. So what is one of the rules of finding identity elements? Remember, one of them is that an element times its inverse will give you identity element. Will that help us to solve this problem? Let's check. So I would say, let's say, let's K be inverse of A, so that A asterisk K should give me identity element. But if I do this, from the definition here, A asterisk K will be equals to A, any place that C B, because K has taken the place of B. So I will replace that with K, and then I'll write this AK. I know that this will give me identity E. So identity E equals to A plus K plus AK. Wow. It does not really give us any tangible results. It cannot give us anything to draw a conclusion on. So this specific, though this is the result, it has given us the result, but we are looking for a value result, a real number result, because this set was defined from set of real numbers. So we need a real number result. This approach has not given us a clue to solve this problem perfectly. So we look for a property that also connects identity. Don't forget, the very most more a property that you should not forget is that if I multiply any element to its identity, it will give that element. Wow. That property was the property we brought and I explained during my explanation session. So I want to use this property, and this is one of the ways that you can also find an identity element at ease. That means I will say, let E be the identity element of A. Identity element of A, or in the set, or in the set. Not just for A, because the identity element of a particular set is only one for that particular set, as far as the definition that is given is concerned. So that means writing A asterisk E, which is by definition equals to A, okay. Remember that E has taken the place of a B from this definition. So I will write this expression as far as that definition is concerned as A plus, that means where I'm supposed to write B. Okay, let me write that place out very well. The definition is given by A asterisk B equals to A plus B plus AB. So in the place of B, I'll put E, which is the identity element. And then I will write AE also. That is the linear equation we have. But A times E will give us A from this is understanding that we had. That means A equals to A plus E plus AE. So I'll collect like terms. A can go to where A is. We have A minus A will be equals to E plus AE. And then we have 0 to be equals to E. We can factorize that place. We have 1 plus A. And this is a 0 law here, which explain, I can use this place to briefly explain that law. If you have two numbers, say x, y, in any way that is equals to 0, if you have any two numbers, just think of any number in your mind now, and multiply them to be equals to 0. Those two numbers will never be equal to 0 unless either one of them is equals to 0. We can say either x is equals to 0 or y is equals to 0 for this principle to be true. So I will say either E is equals to 0 or 1 plus A that is inside the bracket is equals to 0, which would define A to be equals to minus 1. So on this note, we have that the identity element E is equals to 0. Take note of that. Okay. Just want to believe that you understand that explanation. Again, another problem that I would like us to look at is this one. Yeah. We have a binary operation again. Asterisk is defined on the set of real numbers such that another real numbers such that A asterisk B equals to this. This is a new definition. So I would like to write that definition first, or the operator, what it is telling us. It's equals to A plus 2B. Find the inverse of 3. Find the inverse of 3, given that the identity element is 0. So we said that, let's put everything that we have. The identity element is given in this problem as 0. And because of that, we are looking for the inverse of the value 3. So how do we do that? I would say, let K be this inverse. Let K be this inverse of 3. Because if K is the inverse of 3, that means 3 times, asterisk K, give us identity element. I want to believe you still remember that definition. The rule says that if two elements can give an identity element, then one of those elements is the inverse of the other one element I explained earlier. So if K is the inverse of 3, then 3 asterisk K must be equals to the identity element. And since the identity element in this case is equals to 0, then we can say 3 asterisk K must be equals to 0. If you like, you can put that as an equation 1. So but by definition, we know that A asterisk B is equals to this expression here. So it means that 3 has taken the place of A, or I can say A is now equals to 3 and B is now equals to K. So 3 asterisk K is now can be written with respect to the definition given as 3 plus 2K. And also we got that 3 asterisk K is 0. So I'm going to write this other place. I'm going to write this other place. We know that here is equals to 0. So I'm going to write here as 0. That means 0 equals to 3 plus 2K. On that note, we can say that minus 3 is equals to 2K, or at the same time, 2K is equals to minus 3. If we divide both sides by 3 in order to find K, sorry, by 2 in order to find K, divide both sides by 2 in order to find K. We have that 2K all over 2 equals to minus 3 all over 2, and 2 cancel 2. We have K to be equals to minus 3 all over 2. Therefore, conclusion, minus 3 over 2 is the inverse of 3 in this, from this definition. So that is another way examiners like to set problems under binary oppression. So I have just one more problem to solve under this. So the last problem there will be the one I so love very much. And I'm going to solve this problem in two couple of ways. I'm going to solve it the way it is given. And I will also leave it for you to solve it if the identity element was not given at all as what it is given to be. So the problem here says, a binary operation asterisk is defined on the set of real numbers such that A asterisk B equals to A plus B minus AB. So, and we have to find the inverse of this, find the inverse of an element X under this operation. This is the operation they are talking about. Under this operation, when you hear operation, they are talking about the relation, the function that is given here. To find the value of K, to find the inverse of an element X under this operation. Okay. And before we solve this problem, I would still like to remind you of some basic properties of this thing that I've said earlier. If X have an inverse, then I will say let Y be the inverse of element X. So if Y is the inverse of element X, then X operator Y must give us the identity element. Don't forget. An element combined with the operator with its inverse always give an identity element. Or when an element is collected and grouped together with respect to its operator, an element and its inverse is collected together with respect to with its operator, we have an identity element. This one is a very important rules that you must not forget. So I would say this is one of the way you must use to find this problem. So I would say that x asterisk y must give us e. Okay, the e, which is the identity element in this problem, is given as 1. So that means x asterisk y is equals to 1. So therefore, let's write the expression like this, given the definition that it is known. We know that a asterisk b is equals to, we know that a asterisk b is equals to a plus b minus ab. And then if a is equals to x and b is equals to y, then x asterisk, then we say x asterisk y of x asterisk y must be equals to, look at the relation. That means every place you see a, you replace it with x. You have x plus every place you see y, I mean b, replace it with y minus xy. But from the definition above, x asterisk y is an identity element and is equals to 1. So here is equals to 1. So 1 equals to x plus y minus xy. Don't forget, we want to find the value of y because y is the inverse. We said that let y be the inverse. So we want to make y subject of the formula. So move x, this other x to this side. We have 1 minus x is equals to y minus xy. And then y, you can also write it as y minus xy equals to 1 minus x. And if you look at it, y is common here. So let's factor it out. Y into 1 minus x is equals to 1 minus x. The coefficient of y in this case is equals to 1 minus x. So we divide both sides by the coefficient of y. Divide both sides by a coefficient of y, that is 1 minus x that we are seeing here. So if you do that, you have y into 1 minus x divided by 1 minus x. Then on the right-hand side, you will still have 1 minus x, 1 minus x divided by 1 minus x. 1 minus x here cancel 1 minus x. And 1 minus x here cancel 1 minus x. How many times? 1 time. That means y is still also equals to 1. So we can say that the inverse of x, therefore, the inverse of x is y and is equals to, you can just write out the conclusion is 1. Since it's y is equals to 1. The inverse of x is equals to 1 from what we have seen. So, and this has drawn us to the end of this lesson. If this lesson helped you in any way, I would like you to subscribe to the channel because new content will be coming out 2 times in a week. Mostly produce my content on the Thursdays and a Friday. I tell you the truth, the channel is going to really emphasize on standard examination like one German SAT examination topics. And of course, and I'm going to show you how to solve some complex problem and some cheap ways to deal with those problems. So like and comment. If you have any questions under any of the topic I've treated, maybe you don't understand, maybe you encountered a problem and it seems it's difficult and it looks difficult to you, don't be shy to drop it on the comment section. I always address all my questions on the Sunday evening so that on Monday morning you can have access to all of those problems. It will also help you to uh, develop yourself in your problem solving skills and mathematics examination. At this time, I would like to pause here and say, have a nice time.